Take 3. Here we go. Please subscribe. This is the best quality video you will ever see, guaranteed. It's easy, free, and quick. Subscribe now. Do it, yes. But today I'm not going to be talking about polyhedra. And don't worry, I'm not going to be straying away from polyhedra. I mean, I kind of am for now, but next week I'm going to be talking about isociohedra. But now we're going to be talking about infinities, and before we talk about infinities, we have to talk about cardinals and ordinals. So what are cardinals and ordinals? Okay, we're going to have cardinals and ordinals examples. So let's say we have 1, 2, 3, 4, 5, 6 dots. 6 dots. So we have our set. This is our set of 6 dots. And the 6 is a cardinality. So the number is a cardinality of the set. If that doesn't make sense, you should look into that a little bit more, but try it. Grab any amount of objects or books, maybe 3 or 4, and then count 1, 2, 3, 4, 5, 6, how many objects you have. That ending number is going to be the cardinality of all the objects you have. That's what cardinals are. It labels counting, cardinal counting, you get the idea. But what's ordinals? Let's say you have shopping, let's say 1 milk, anything. 2, I don't know, how about pasta? And 3 apples. This 3 is the ordinal. It says how it's ordered, because 2 could have been apples, but the ordinal of the apples, that set of apples, would now be 2. So if you were to have 3 of 10, 3 would be 10 apples, 10 would be the cardinal, and 10 would be the cardinal, 3 would be the ordinal. Ordinals label things that they're ordered in, and cardinals label things 1 to 1, how they're counted. So we got that out of the way. Beautiful. Now I can get rid of all of this. Alright, so now we're going to talk about the first infinity, which is aleph null. So let's say you have a line that's 1 meter tall, and half a meter away you draw a line half a meter tall. Third of a meter away you draw a third of a meter tall, and so on. Another fun fact, this is called what's it called? Yeah, I forgot, but that's not what we're talking about. We're talking about infinities. So we can label these 0, 1, 2, 3, 4, so on. Makes sense, right? But what if we add another one? What if we add another line? Well, instead we could just start here and shift everything like this. we could just shift everything, so now this would be 0. Alpha plus 1 plus a plus any number, because you could just shift everything that amount, is still aleph null. Because even if you had the alpha null amount things, because you could just add 0, 1, 2, 3, 4, 5, 6, 7, 8. Also, you could just take every other line and then move it up and move it. You can alpha null plus alpha null is alpha null. Well, what if instead of doing that, we have our lines and we have this, and we have to start here, so 0, 1, 2, 3, 4, 5, and so on. Well, what comes here? We've already used up all the numbers, so we have our first ordinal infinity. Omega. This is not a joke. This is not a joke. Omega is the next symbol. I'll draw that better. Omega is the first symbol you will need to count ordinal infinities. You have omega plus 1. You could have omega plus omega. And here we fall into a dilemma. Well, not really a dilemma, but I need to teach you 4 things. 2 axioms / hypotheses, and 2 mathematical properties or things you can do. First, we have the Axiom of Infinity. What does that state? The Axiom of Infinity states there is only aleph no, or however you spell it, but aleph null. There's only aleph null. There's only, I can't type. There is only all the integers. Oh, there's only all integers. So, like, if you're going to take the rationals out, that's basically what this says. And you might think, well, we're going to have to make a new axiom or / hypothesis every time. And by the way, throughout this fit, well, not throughout this fit, because these are basically the only 2 things that we're going to use. But when I say axiom, you can also think of it as hypothesis. But this isn't really, well, it was a hypothesis. This was an hypothesis, but the thing is, it's been proven wrong. And you were probably thinking, do we have to have a new axiom every time we add another aleph null amount things? Well, luckily, no, because the axiom of replacement. Now, you're probably thinking, why are you talking about the axiom of replacement? What is that, and how will it help us? Well, I'll tell you what it is, and I'll tell you how it will help us. To get to higher and higher infinities. So the axiom of replacement states that with any set, you can replace all the objects in that set and the resulting set, and that's going without saying, but objects. With any set, you can replace all the objects in that set with other objects, and the resulting set will still be a valid set. Now that sounds really weird. With any set, you can replace all the objects in that set with other objects, and the resulting set will still be a valid set. What does that mean? Let's say you take the set of 1, 2, and 3. Then you can replace the numbers in that with, how about negatives? -1, -2, -3. You can replace it with apples, bananas, anything. And that will still result in another set. That should help you. If you have a set of water bottles, you can replace those with glasses of milk, and you'll still have things. It's not like you just remove things, you just changed those things. That's what this axiom is trying to get at. So remember that, because that will, no, you don't need to remember it, because it'll probably be, oh, sorry for hitting the mic, but I'll probably be going back to the Axiom of Replacement. So this is a helpful thing to remember. Axiom of Infinity, you don't need to remember, but Axiom of Replacement is something you can remember if you want to teach other people about this, which I always recommend you do. If I teach you something, I strongly recommend you pass that knowledge down to someone else. But now we have that. I'm going to teach you about 2 different mathematical operations that school usually really doesn't teach you about, because sometimes they're not too important. First thing is power setting. So the power set of the set. What does that mean? Let's say we take the set of 1, 2, and 3. The power set of that set is all the subsets you can make of that set. Well, if you want to be more precise, the power set of any set is the set of all the subsets you can make of that set. And what do I mean by that? So you can have the set, so we have a full set, and we have the set of nothing, another set of 1, another set of 2, another set of 3, another set of 1 and 2, another set of 1 and 3, another set of 2, 3, and another set of 1, 2, and 3. That is the power set. If you notice, we have 8 things. 1, 2, 3, 4, 5, 6, 7, 8. And again, if you forgot the definition, the power set of a set is all the subsets you can make of that set, including the set itself. I forgot to mention the set itself, but yes, the set itself does count as a subset. So, there. But we only start with 3 things. Hold on 1 second. I thought I was gonna sneeze for a second. Alright. So 8 does not equal 3. 8 does not equal 3. It is 2 to the 3 after, so that means the power set of the set equals 2 to the s. Cool, right? That is what power setting is, and that's what it equals. There. I am not going to be proving it. You can see a proof, but I have no idea how to prove it. Let's get to tetration. Let's get to tetration. What's tetration? Tetration is, so you know how we have like 1 plus 3 equals 4. Then we have multiplication, like 1 times 3 equals 3. And then we have exponentiation, 1 to the 3rd equals 1. But what about tetration? Well, look at the pattern. We have addition, repeated addition, repeated multiplication. What about repeated exponentiation? So 1 to the 3rd. So 1 tetrated 3 times is 1 to the 1 to the 1, which is 1. That is the definition of tetration. So we have that. Let's say you take omega. And you're going to be, from now on, probably depicting that with the W, because I do not know how to draw anything. So I'm going to be depicting omega as this. Let's say I drew that way too far. You take omega and you power set it. And you power set that. And you do that on omega times. And then you saturate that omega times, saturate that omega times, omega times. Then you power set that, you power set that, and repeat this in omega amount of times. You get a huge number, but what if there's something you can't reach from doing that? We have reached Aleph 1, also known as Epsilon 0. We are not done yet. I have said that already, I'm pretty sure, and I say that again. We are not done. We still have way more to go. So, bam. This is Aleph 1. Now, let's expand off of that. Let me make sure I've been recording the whole time. I have. Great, yes. So we can have, okay, I'm going to be referring back to the Axiom of Replacement. So I hope you have remembered that we can take something like 1, 2, 3, 4, 5, and then 2. And by the way, I'm going to be replacing Aleph with N because it's way easier to draw. We have Aleph 1, Aleph 2, 3, Aleph 4, then Aleph 5, and then you get to like Aleph Omega 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 Omega. Then you get Aleph Omega 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 Aleph Omega Aleph Omega 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 Ooh, I've said it 2 times and I've said it again. I'm gonna say it again. We have still not reached the end. We are almost at the end though. One more thing I need to tell you about. Unreachables. We have the unreachables. You can't reach them from below. Like this, you can't reach even from power setting alpha times Tetra that with alpha and alpha amount of times. I'm gonna repeat that by an alpha amount of times. That doesn't get you to an unreachable. Nothing will. Unreachables are like, I don't know. They're like space. You're probably never gonna be there. And if you do, then it's most likely hypothetical. And in this case it is hypothetical because, again, they're unreachables. And after unreachables you have things like hyper larges, hyper larges. You have things like hyper huge, infinities like that, and then you get whole trees of infinities. And infinity is a huge mess. Why am I talking about it? You're probably wondering. Because, oh no, infinity is super cool. Yeah, it's super cool. And again, please subscribe. Please subscribe for the highest quality content ever guaranteed. Yay. Please subscribe for the highest quality content ever guaranteed. Yay. Well, I am finally free and it's 4:20. Nice. Bye.